Hello?
Yeah, can you hear me, Professor?
Yeah, I can hear you.
Uh, a very warm evening and welcome to our SBC.
Yeah, thank you, thank you. Thank you so
So
much for
we'll
inviting
be
me.
waiting for some time more for
Sure,
others
sure,
to
sure,
join,
sure. No, no
and
issue.
we'll join. We'll start shortly.
Sure, sure. No problem.
Okay. So I believe we can start now. Professor Medhi, you're here?
Yeah, yeah, sure. I'm here.
Yeah. Okay. Just give me a minute. Okay. So very warm welcome to all of you present here, and a very good evening to all. So today we are gathered here for the webinar on SDN for data center networking organized by IEEE Kharagpur section, Computer Society Student Branch Chapter, that is the IEEE KGP section CSSBC. And as our esteemed speaker today, we have Professor Nabajyoti Medhi, who is currently serving as the assistant professor from Tezpur University in Assam, and who will be delivering a lecture on the SDN for data center SDN for data center networking. So, on behalf of all the participants here and on behalf of everyone here at IEEE KGP CSSBC, I would like to extend my hearty warm welcome to you, Dr. Medhi. Thank you so much for coming, and we hope that it will be an interactive session. Myself, I am Konteo Sarkar from IEEE CSSBC, and I will be your host for this particular session. Okay.
Thank you, Conte.
Before we begin, actually, I would like to introduce you a bit more to our audience. So, as a very short biography, Dr. Nabajyoti Medhi is currently serving as an assistant professor in the Department of Computer Science and Engineering at Tezpur University in Assam. He did his PhD in Computer Science and Engineering from NIT Meghalaya. He did his MTech in IT from Tezpur University and BTech in IT from Assam University. His field of specialization includes software-defined networking, that is SDN, network function virtualization, that is NFV, network security, and wireless networks. He has over 10 years of experience in R&D in teaching, and prior to this, he was also an assistant professor at NIT Silchar and NIT Meghalaya. Dr. Medhi has got the certification from ONF, that is the Open Networking Foundation, which is the current custodian of SDN protocols currently worldwide, we can say. So he received the ONF certificate as an SDN associate in 2016, and he is currently also excuse me. He is currently also leading a project titled Ensuring QoS in Internet of Medical Things using software-defined networking, which is sponsored by METI, that is Ministry of Information Technology, Government of India. So with this, I would again like to welcome you, Dr. Medhi, and you can start your presentation and your talk. So I would like all the participants to please listen to it in a very attentive way, and if you have any questions, the question and answer session will be held at the end. Over to you, Dr. Medhi.
Thank you, Conte, for the brief introduction, and that was really nice. And first of all, I thank you to IEEE Computer Society Student Branch Chapter of IIT Kharagpur for giving me this opportunity to speak to you on a particular topic. Thank you for the invitation. So, okay, looking at the time constraint, I would like to start my presentation. So, okay, I'm just going to share it. So anyhow, okay, I'm sharing the complete screen, I believe. So is it visible to everyone?
Yeah, it is visible clearly.
My screen? Okay, fine. So okay, so as you know, I believe that many people are also working in IIT Kharagpur and in many other places on software-defined networking. So as a basic definition of software-defined networking, what is software-defined networking? I'd like to say that okay, the whole story started in 2009 and in Stanford University when one of the PhD scholar there named Martin Casado, he was working under Professor Nick McKeown, and when he graduated, when he published his thesis, he published it as a title with ethane. So with the model of ethane, he first actually provided the idea that okay, we can have actually softwareized control. We have a central control from a device, and we can control the whole network. Because earlier to that, even the software-defined ideas were not new, because we have a lot of software-defined things earlier. Because like software-defined radio and software-defined, so many other things were also available. But software-defined networking, this came up with a big hype in 2009, and gradually people started okay, because the whole networking industry was more towards vendor-centric, completely hardware-centric, and there were very less options of innovations in most of the places by the customers, and also in the research community. It was completely given to the vendor. They can only innovate. They can only do the things that are required to the customers. So once the model of E10 came up, then they further we from the Stanford University, they further grew up with the community, and they developed it as a protocol called OpenFlow. So with the idea of open flow, there came the idea of matching action and counters. Suppose I am sending a packet to a particular device, any networking device. So already we have like if it is a layer 2 device, I will have the switching table. If it is a layer 3 router or any other layer 3 device, it will have some network information base, routing information base, or any other form of routing table. And again, with the software-defined network and open flow, there also came another concept called flow table. So the flow table is nothing but it's a kind of switching table only, where you have more where we are given more ability to control and to program it from a central device, and that can be done by ourselves. So as a viewpoint from the viewpoint of a customer, we can do our own programming, we can design our own software, we can design our applications, and we can implement those things on the networking devices right from our device. So with the evolution of OpenFlow, then came the idea of whole software-defined networking as a big domain. So and software-defined network came up with a lot of other APIs, a lot of other protocols, and then people realized that okay, software-defined networking having a good impact in the campus networks. So gradually, there are a lot of R&D teams. They started working on software-defined networking for bigger domains like data center networks, wide area networks, and all other places. And most successfully, it was Google in I think 2013. They deployed the software-defined networking for the first time in the wide area network. And they called it as a B4 architecture. So I think already, if you search in Google, it is available in their website. It's also as a publication, it is available. So Google was the first one to
excuse me, Dr. Medhi, just sorry to interrupt. Yeah, are you changing your slides? Actually, it is not.
No, I'm the first introductory slide.
Okay.
Go to the next, I believe.
Sure. It is.
Yeah, sure. You can see the second slide.
Yeah. It's seeing. I thought that it is not being reflected.
Oh, no.
Maybe the screen froze. Okay, sure. Thank you.
Yeah, sure. Just
Sorry
let
for
me know.
interrupting.
Yeah. So Google, actually, I told you that Google came up with the first implementation of B4 networks, the first wide area network implementation of software-defined networks, and they implemented software-defined networks controllers for their inter-data center networking. Like they for a particular data center, because their data centers are located in multiple locations on Earth, and for the inter-data center network traffic engineering, they started using the software-defined network and OpenFlow. So that was the first large-scale deployment of software-defined network in the wide area network. So right from the 2013. So okay, today in this particular talk, I will just try to deliver a little bit of data center networking, some issues and challenges, and software-defined network OpenFlow. And I'm just limited to OpenFlow right now because it is one of the most popular, like commercial API that we are using. And there are a lot of others, but I think that takes a lot of time to discuss everything. So I'll be limited to the OpenFlow only. So if you think about data center networks, then of course we have a picture of thousands of servers, switches in racks, and a lot of VMs are moving. A lot of VMs are located within the servers, hypervisors, and we have a large unpredictable traffic moving within the data center. So there is a huge, like chaotic network, I can say. And in this particular work, I'm just showing that, okay, software-defined network and open flow, how you can use it for the data center as a fabric. Now, in this particular work, there's a particular term called fabric is coming up here. Fabric means it's a particular topological design coming up along with some particular software and applications to support the overall traffic scenario. So it is not only a software, it is not only a particular hardware design. So it is a combination of both to give you a solution to the particular problem. So, okay, now we come to the idea of virtualization. So as you know, in data center networks, virtualization is a big challenge, I believe, because on an average, every blade server where they were putting in the rack, so each and every blade server, they're containing around minimum around if we have today's Xeon core processors with 128 GB RAM and that kind of configuration. If we have in our servers, then we are expected to host around 20 to 30 virtual machines running at the same time in the servers. And in order to handle the traffic, load balancing and all, the VMs sometimes migrate from one server to another server, either in a live mode or in a passive mode. So what do you mean by live mode or passive mode? So when the VM moves from one location to another location, that is one server to another server, without changing the state, that means if the VM is already active, it will maintain the same state and copy the same state in another server. Then only the virtual disk will be moved to the another server. So that is one of the very challenging VM migration that we call as a live VM migration. And another one is passive migration that we stop. We actually fix the VM in particular state, and then we migrate the VM to another server. So that is comparatively easier than live migration. And we have some idea of multi-tenancy, because in data center networks, like if we say tenant is a, you can say it's a completely private area to a particular network where multiple tenants, multiple locations, multiple segments of the networks are there. Multiple segments we can call the multiple tenants, and they have their own communication policies, like how they will forward, how they will block each other. So they have a lot of network segments within the same network, depending upon the privacy requirements. So maintaining those things are not easy every time, because if you consider a big data center like Google, there are millions of servers are running at the same time in one data center itself. In that case, maintaining these, troubleshooting all these failures are a really big challenge. So what kind of traffic generally we have in the data center traffic? Typically, we have two types of traffic. One is called like north-south. North-south traffic means, suppose a Facebook user is connecting to the Facebook server. So that is coming from the customer to server, customer to server. So that kind of communication is the north-south traffic. So it is coming through the wide area network to the data center network router and coming to the server, and in vice versa, opposite direction. And the major challenge doesn't lie in the north-south traffic. Rather, major challenge will lie in the east-west traffic. The east-west traffic means there are some part of traffic that is flowing within the data center. That is, one example like VM migration. As you already know, the VMs are moving from one place to another, one server to another server. And also, maybe like I'm getting a Facebook request. That Facebook request, friend request. This is coming as a north-south traffic, and one Facebook request is requiring actually updating a lot of databases, a lot of database tables, a lot of databases placed in a lot of servers. So if you can imagine, like one Facebook request, friend request, can create around 10 times of the whatever traffic is coming in the north-south, it can be around it will generate 10 times the volume of that particular north-south traffic in the east-west traffic. So east-west traffic is always very much larger as compared to the north-south traffic. And if you are using load balancing, if you are using traffic engineering, then those will issue some redirection of the HTTP request, and that will create a very much troublesome scenario within the data center. So if I truly say that what is the major challenge in data centers, it is not the north-south traffic. It is not that Facebook users are increasing. It is not that a particular service having a lot of users, not because of that. It is because of the amount of data that is flowing within the data center to synchronize with the applications. And we have large number of flows. We can say a huge amount of traffic flows are flowing all the time, and traffic pattern is always random. Most of the time it is random. We do not have a fixed pattern. Like we do not know, depending upon the application, you do not know when the traffic will be high, when the traffic will be low. So it can be quite random all the time. So I just show you some typical. I've given some of the public references below, and I took out some of the images that will be good to represent. So the links are already available, references are already available. So this is the east-west traffic. From the access level switches, multiple access switches are communicating to each other, and the north-south traffic is going from the access switches to the core switches to the routers, and again coming back to the from router, core switch, aggregation, and access. This is a typical typical data center network topological architecture that is also known as close architecture. There was a computer scientist named C. Close. I forgot the complete name. So he actually researched on this particular types of topologies where there are multiple hierarchies of the topology, like depending upon the capacity of the switches and devices, we have a multi-layered architecture. Suppose we have a 3-layer architecture in this particular diagram. We have a core layer, we have an aggregation layer, we have an access layer. And in the second diagram, we have a spine leaf topology. That is also popularly known as a spine leaf. This is also a 2-layer closed topology. And if you physically look at the actual position of the closed topology in the data center itself, then it will look like those kind of diagram that are shown on the right side. There are a lot of wirings and a lot of racks are placed all together, making a complicated closed topology. And we have a lot of cooling requirements. We have a lot of electricity requirements to support the cooling, because in a data center, overheating may be a big problem. If there's a congestion, we have a lot of heat generation, and if there's overheating, it can destroy a particular port, and thereby it can destroy a complete switch also. And it can lead to a huge congestion scenario. So we need a lot of cooling in the data center, and that consumes a lot of electricity. So maintenance is not that easy all the time. So it is very much required that if we understand a particular failure, if we can detect the failure from a central device, that can be a very much that can be a really good benefit, because it can reduce the manpower requirement in the maintenance, and also it will make the whole system easy to handle and easy to manage. Now, okay, if we go to looking at the evolution of data, and as we know, if we look at the networking from 90s, when we have laptop in 90s or in 2000s, early 2000s, we were purchasing the laptop with fast Ethernet that were very much known as 100 Mbps Ethernet that time, and 2006, 7, 8, like that, who purchased laptop at that time. So 100 Mbps, we say fast Ethernet. Now, what is happening right now? So now we have a terabit Ethernet. So terabit Ethernet has already come, and we have a lot of evolutions are happening. And as you know, the Facebook evolved in 2003, I believe, 2004. Yeah. So, and when the user base increased, they realized, in one of the article I have shown in the link below, they realized the requirement of terabit Ethernet, because they saw the gigantic increase of the traffic all the time because of the increasing number of users in Facebook and all. So they published there's a published article like Facebook dreamt of the terabit Ethernet in 2010, and that dream of Facebook came true right now in 2020s, especially when we had the first version of 100 gigabit Ethernet in early 2010 and 2010-11 or in between that. We had the 100 gigabit Ethernet. Gradually, we had the 200 gigabit Ethernet. Now, and in a commercial scale, we have the maximum capacity in a commercial scale that is deployed in the data center, that is 400 gigabit Ethernet. So we call it. We have the notations for Ethernet. So we have 200 gigabit Ethernet also. 800 gigabit is also under deployment, and 1.6 terabit Ethernet is also under experimentation. So it will also come very soon. So we have some IEEE standards, as you know, like IEEE 802.3 for all the Ethernets. So in 2017, it came up with the 400 gigabit, the basic version of 400 gigabit. There is the 400 gigabit G-base SR16. So you already, I think, know the Ethernet notations like 400 gigabit baseband, and all the cabling and all those things are denoted at the last hop. So there are a lot of combinations. Like there is a 4-lane architecture with DR4. There are 16 pair cabling, the single mode cabling, single mode fiber, I believe, or sorry, multi mode fiber of 16 pairs, that is SR16, and single mode fiber for 4-lane architecture of DR4. And so there are a lot of, like a lot of architectures are present. And 802.3 CK in 2022, it got the standardized. So it is also the first active, chip to module architecture. 4-lane 100 gigabit means 100 gigabit per lane with 4-lane architecture for Ethernet. So you can see the capacity increments in the last 10 years or last 20 years. You can see like in last 25 years, we have evolved from 100 Mbps to right now 400 gigabit Ethernet. So that is a very huge rise in the Ethernet. We have 802.3 DF. That is the first stable implementation of 100 gigabit Ethernet. And also, as I told you, 802.3 DJ is giving the 1.6 terabit Ethernet, and a lot of 200 gigabit parallel technology is also coming. There already some vendors are manufacturing, but yet it is yet to be deployed in a full scale in the data centers. And some of the examples I gave you, very popular, like Nokia 7250 interconnect routers. If you go and check the specifications, I've just given for example, like that will be more interesting, because without example, things are not good. And like I'm just showing a sample specification of that particular interconnect router. Like you can see, they have a system capacity of up to 230.4 terabits per second. They are implementing 40 gigabit, 100 gigabit, 40, 25, 10 gigabit, all the interfaces available, and their maximum is 400 gigabit. They also implement one of the very popular open source, implementation of the router that is called SR Linux. Is very much popular as a network operating system. You can go to the GitHub link, and many of you, like suppose you are trying to, do some research on to develop a customized switching architecture, switching infrastructure. Then you can go to the source code of Nokia SR Linux, and it is a very good implementation, and it is basically an unmodified Linux kernel. And it gives a lot of model-driven design for the switching architecture. And it is also, you have a Python-based CLI and state-of-the-art NetOps development kit, and NDK is available there. And it also has default routing features of IP, like multi-protocol BGP, EVPN, VXLAN. And we also have the hardware extendability feature. So you can deploy this particular network operating system on in any of the open networking hardwares. like open network install environment that we call ONIE. So you can install in any of this supportive open networking install environments, and you can extend it to the hardware also. So it is one of the very popular going on right now, and you can explore it further. And it is most popularly a state sharing architecture. Having a publish subscriber architecture with sharing the states among the Linux applications. So anyhow, that was just an example I'm just showing you. Like commercially, that is not the only one. There are multiple architectures are there. I have not included here. So what do you mean by software-defined networking? Like you already know, many of you do research, and I hope the audience today, they have some like maybe having some basic, they already working with SDNs. So like we have a separation of control plane and data plane, which was earlier integrated together. Now SDN is trying to separate it out, separating the control plane out of the data plane. Now we don't need an integrated operating system with the data plane. Rather, we make a programmable operating system with the particular device, so that we can program the control plane by our choice. We can change the routing protocol by our choice, and we can change all the switching, routing, whatever we want from at any instant, at any point of time. We can try to implement it. And the management is also very easy, because if you can program by Python and you are running your programs from a laptop, you are running the whole network, that is much more convenient. We have two different kinds of APIs, that's called southbound, northbound, and also we have some eastbound, westbound, whatever, but we categorize into northbound and southbound primarily. So northbound is nothing but the most of the network applications are talking to the control plane. If the network applications are talking to the control plane, they communicate through the northbound APIs. Like we use a lot of REST APIs and other, so many other APIs that will communicate from the application to the switch memory or switch operating system. Whatever protocol you use there, that will be northbound. And southbound, because southbound is all about the control plane to data plane communication, like whatever instruction you're giving from the controller device coming to the control plane, and control plane is instructing the data plane. Data plane is nothing but the actual forwarding hardware, where actually you have the ASICs, you have the forwarding implementations, and if you want to incorporate new policies, your control plane will install in it. So those APIs are called southbound APIs. And one of the very popular example is OpenFlow that we are already using. I think many of us, we are already working with that. And we also work with OpenFlow a lot. Like OpenFlow has a lot of versions, like version 1.0 to now version 1.6. So there are a lot of features we have already. So what are the types of SDNs? So if we just look at the types of SDN, then there are some major categories we can have. We can have one open SDN. So open SDN has a centralized control plane and uses OpenFlow for the southbound API. And if we use one of the very popular distributed controller that is called ONOS and Big Switch networks also having the implementation of SDN. So there are some examples of this kind of implementation where we assume that we have a centralized control plane and we are using OpenFlow as a southbound API. Most of our research community, especially like what we do in the academic research, most of us are very much limited to this particular part of SDN. We call it open SDN. And another SDN called overlay-based SDN. So, like overlay network is nothing but one network on top of another network, and the upper network is hiding the network behind. So that kind of overlay, like we know about the VXLAN, VLAN, those kind of VPN, those kind of overlay networks. And it has, using the overlay network also, there are some solutions of SDNs are also available. So SDN is not only OpenFlow, SDN has a lot of other implementations like Juniper Contrail, NEC VTN, NSX from VMware. They have some overlay-based SDN implementation, and most of them are commercial scale they are doing. So in commercial fabrics, they are trying to implement this kind of designs. One is called API-based SDN, or we also call it unopened SDN. So This is all about network programming, and we use the network programming APIs like netconf, oplex, SSH communication for southbound APIs to allow programming of the networking nodes. So we are directly programming the network nodes using this kind of APIs, uh, and we may use southbound APIs there. This kind of southbound APIs also can be used. And Open Daylight controllers support that kind of unopened SDN, Epic DC, EM, Tailor by NSO. These are examples of the implementation. You can go and search in the ONF, the Open Networking Foundation website. There are a lot of examples and projects given and detailed. So you can go for the detailed description of that. And the last one is the automation-based or hybrid SDN. So it actually uses the legacy network equipment and also covers the SDN-enabled feature. And if I say that most of the commercial switches that we are buying, or most of the commercial appliances we are buying with SDN support, most of them are hybrid or automation-based SDN. So they have the ability to switch from legacy features, and if we want to disable the legacy features, we can directly switch to completely SDN-based or SDN-based to legacy, or we can have both working together. Like we have, we in our lab, we have the Allied Telesis SDN switch. We have the mode, we have the hybrid SDN abilities there. Like we are having a 16-port switch. So what you can do sometimes, like 8 ports out of the 16 port, the 8 port we are making complete pure open flow part, and another 8 port we are putting as the completely legacy part. And there's another feature we have that is called ONIE. Just now I told you the Open Networking Install environment. So these kind of environments are giving the ability to install our own operating system on top of the hardware switches or hardware routers. We also have one switch. We have the Dell EMC ONIE switch already running in our lab. So we have installed the OpenSwitch operating system. On top of that, we install the OVS. Like Open vSwitch is one of the very popular agent, software-based agent that supports the switching and OpenFlow. So we are having this kind of environments also present in our lab. So, and that is very convenient because that is not very much fixed with the operating system. When the operating system is already given by the vendor, it creates a lot of challenges because we cannot configure a lot of things, and we have to be limited in our approaches because features are always limited in doing that. So the ONIE switch really gives a lot of feature, and it gives a lot of freedom to us to work on a particular open environment. So these are, like pictorial comparison I can say. Like we have a SDN application on top. We in OpenFlow based SDN control. We have the controller. Controller is using OpenFlow to control the forwarding, and API based SDN and overlay based SDN. We generally use a lot of virtual networks because we are using overlay. The virtual networks are very popular. And automation-based SDN, like we have a lot of agents, tools in the middle between the SDN application and the control. So, and then control is directly connected to the forwarding. So you can have different types of implementation of SDN based upon your requirement. So we have some very popular architectures like OVS, one of the very popular uh, software switch architecture, or I can say precisely software switch agent. So this is also coming up with a very popular emulator called Mininet. You can also install in your operating system OVS, and you can get all the virtual switching benefits from the OVS itself. We have also OVN. So OVN is nothing but a similar architecture that uses OVS and OVN controllers to facilitate the cloud architectures. Like most of the time you heard about the OpenStack cloud architecture. So in OpenStack cloud architecture, we use multiple OVMs, and that give like each and every node will have the local controller and local OpenFlow switch. OVS, they will have some modules of OpenFlows. So that is also an implementation, a cloud-like implementation, and like OpenStack Neutron plugin that has the implementation of OVMs. And nowadays, it's also very much popular, like P4 programmable NICs. Like P4 is the, it is completely programming a like protocol independent packet processor. So what you can do, you can directly implement the debugger. You can directly do what, like not like OpenFlow. Like OpenFlow will talk to the controller, controller will talk to the control plane to data plane. Not like that. What do you do? We directly debug the data plane. So we do the packet processing, and we just implement. We can have some programmable NICs. We can also implement this in FPGAs and all, some other hardware boards also. Like NICs will have the direct implementation of the programmability. Like we can implement our policies. What we can do, we can compile our policies, we can put the results of the policies, and those policies will be applied by the forwarding machine. So this kind of smart NIC architectures are also available with FPGA, with NIC and GPU, with P4. So a lot of things are available nowadays for researching in SDN. So OpenFlow, I will not discuss too much about OpenFlow because I have to look at the time also. I'll try to finish by 1 hour. So OpenFlow is a very popular southbound API. So it is in higher versions of OpenFlow, like OpenFlow version 1.2, 1.3. We have a lot of features like pipelining. We have features like flow table, multiple flow table. So what is the benefit? In one switch, if we have multiple flow table, we can do multiple operations, multiple matching and action, in different tables, and we can have more number of filtering. It is possible to do in higher versions of OpenFlow, especially from OpenFlow version 1.2 onward. So we can have group table. We can now not only one action per flow, we can have multiple action per flow. So those kind of features are making OpenFlow even better and more customizable and more flexible in terms of the applications. You can have a lot of security applications. You can have a lot of networking routing applications. So it is giving a lot of benefit from the OpenFlow. A OpenFlow flow table, how does it look like? Typically, it is a very common design that each flow will look like a combination of rule, matching rule, action, and some counter-based statistics. So there are multiple flow entries are available, and you, based upon your memory size, that we call ternary content addressable memory, that we use for storing the flow tables in OpenFlow switches. So based upon the size of the TCAM, your number of entries can be supported. So if you want to support more, you need to have more TCAM. Now, why we use TCAM? Because TCAM is like faster processing as compared to the static RAMs that we can use in the switches. So what is the benefit of a controller here? So controller can think of the complete topology before actually the networking operations are starting. So it will use some discovery protocols by itself, and it will discover the topology. It will have a clear picture or a global picture of the whole topology. So that is the visualization of the OpenFlow controller. And for your reference only, I have just shown some of the very popular SDN solutions that are very much popular nowadays, and not some are very new, and some are also running from a long time, like Cisco Meraki. Meraki was acquired by Cisco, and Meraki was very popular in SDN solutions. So they provide like a lot of add-ons and integrations for your campus networks, your small data center networks, Cisco Plus Network as a Service. So in 2021, it was launched, and it provided a lot of storage security and support integration with the cloud using the software-defined network service. So you can have some code if you're interested to buy or something. You can have the code. You can go to the website. And Cradlepoint Net Cloud is a part of the Ericsson now. So it was actually made like most of the LTE network features. It is giving the wireless network environments using the software-defined networking. So a completely programmable network that is based on the wireless LTE networks, like also the 5G networks, WAN, and IoT using the one SDN platform. So that is very interesting. We're working in IoT and 5G or LTE networks or other types of LTE networks. They will be interested to have this solution, Dell SDN solution in 2019. So they have the EMC offering. So as I told you, one of the we are also having one of the Dell EMC solution here in our campus. As I told you the architecture already. So we are also using one of this. So they have a uh, uh, they have a basic implementation of data center network fabric orchestration and network management. And we have IBM SDN services that is also providing for large scale servers and especially for the cloud networks and data centers. Juno is like from the Juniper Networks, an AI networking and cloud technology company, and they provide the SDN solution. And as you know already, like Juniper has their own operating system, Juno is. So Juno is Space is the fabric they provided, and especially very popular for the campus networks. Messaging from Comcast. So they provided again. Sorry. So this Messaging integrates the public and private cloud into a fully managed and co-managed cloud. So ultimately, we have a lot of integration of the cloud networks that can be done, managed by the software-defined network. NOS networks, and it is basically from the Nokia. Many people may be knowing it. So they have, they're very popular for the routing for the router operating systems, and they provided, like the SDN solutions also. Pika 8, and if you interested 5 6 years back, so Pika 8 is one of the very small startup. They become very popular with their Pika 8. I think I forgot the name. They have a SDN starter kit. They demoed it in one of the editions of, I think, one of the, I don't know, like sitcom or uh, uh, whatever sitcom, might be a sitcom or some other conference, I forgot. So they developed a very they provided a very small application. They provided a very popular, very simple architecture called SDN starter kit. They use the Ryu SDN controller. They have their own PIC OS operating system, and they were marketing with that. They become very popular right from that particular point. So, and Riverbed still connect. They also provide some centralized platform for software-defined network, and especially for again the cloud-based solution for this. And now we also have the idea called software-defined data centers. So this kind of solution that I just told you, so this can be applied in small-scale data centers, and they will provide you reliability, security, and simplified hardware management, cost effectiveness, and vendor-specific, vendor independence. So that will give you a lot of benefit. And see, I think I will try to skip some of the part. If you like most of us from the research community, nowadays it is not the distance between the research community and the and actually your industry is now not too far. Like with the advent of SDN, now research and academic research and industry research, they can run parallelly, and that is why a lot of good researchers has came in last few 10 years and last 10 years around. So there are some name of the papers, and one of them was my paper also, like the last one, the Oscar. You can search in Google Oscar OpenFlow. Yeah, that paper published in IEEE Communication Letters. So what actually I did, this is providing a very simple open flow based network fabric by using a virtual MAC addressing, a layer 2, layer 3 hybrid addressing we are using, and we provided the architecture for that. So, okay. And data center network fabric with SDN, one of the very popular example I'll give you, like Juniper Cloud Native Constraint Networking, that is also called the CN2. So CN2, it is a hybrid SDN for, for automating the creation and management of virtual networks. It's a hybrid SDN supporting a lot of architectures like Kubernetes, OpenShift, OpenStack, and advanced routing, overlays, a lot of virtual networking and all. And like the CI/CD pipelining, like like continuous innovations and all those things, development and integrations through the GitOps. They provide the facility of that, and we have a web GUI based real-time visualization in that. So if someone is not very much fluent in programming and all, they can go with the CN2 solutions, and they can have the basic idea of how Fabric actually works and in a larger network. So, okay, these are some challenges, of course, in data center. Like addressing is a big problem. You cannot go completely L2, you cannot go completely L3. You cannot follow only IP addressing or IP routing. You can neither follow IP routing only, nor your L2 based flooding. So you should remain somewhere in the middle, and you should use some hybrid routing and forwarding structure, because none of them are completely suitable for a large scale data center networks. So there are some issues with the scalability, reliability, and of course, we have some research that was done quite earlier, and that is based on the hybrid addressing. I will try to skip these parts. Um, so, okay, this is one of the very old papers, but very interesting because it is one of the very innovative idea also, like idea of the routing bridges. Many of you may be knowing that most of the bridges we have, the bridges, the L2 bridges, they have the ability to do operate the forwarding and all in layer 2 only, layer 2 flooding in the L2 domain. But when the routing bridges came up, they had the innovation, like they had the ability to work not only in L2 but also in the L3 domain. So that gave a lot of good applications, like Cisco data center network fabric 6 years, 7 years back, called Cisco Fabric Path. They implemented the trill control plan. They're still operating, like brokered VCS. They also work with the trill architecture. And trill architecture is nothing but a transparent interconnection of a lot of links for a dense network that uses the R bridges. I will not go into details of that, but you can go through the link for the details. We have some other research articles, and one of the article that was by me also as a part of my PhD work that time. So you can go to the reference, you can go through that, and I think this was the summary is that we use the OpenFlow for to give a hybrid addressing architecture for the data center networks. And we did the implementation inside Mininet only. One of the sample topology available in GitHub also. I have shared the link in the PPT, so you can also check. It's very, very simple. So we created the topology inside Mininet, and we just implemented using the floodlight controller. We implemented the hybrid addressing mechanism for data center routing. So that is what all about. So a sample data center closed topology we have taken, and we divided the segments of the networks, and we implemented the hybrid addressing mechanism out there. You can go through the paper for details. And so we have some module for ARP resolution. The controller will do some local ARP resolution. And actually the idea is that whenever the actual forwarding taking place in the L2, between the segments or among the segments, the forwarding is taking place in the L2 domain. But within the segment, the forwarding will take place using the IP routing. So that is the benefit. Within the segment, IP routing, among the segments, it is L2 forwarding. And when we do the L2 forwarding, we do not use the actual MAC address. We use a virtually assigned virtual MAC address that will give the idea of the location also. Because as we know, MAC is completely flat address. It doesn't give any location. But we use the MAC, that's called virtual MAC, that will give you the location of the particular server also. So with that, that was a good idea, and of course that took a lot of time to implement, and also like around 2 years of my PhD time to implement only this particular part. And actually, after the implementation, it was good. It was working good, and I thought that okay, maybe I can show you a little bit of that today. So that we coined a name called Oscar, and there are some of the comparisons with the existing work that time, and some of the results, of course, in terms of throughput and control packet volume. So we had some benefit because that was more flexible combination of L2 and L3, and got some more benefit with large number of flows. But of course, our limitation was not completely we did in Mininet. We did not have that many hardware switches that time, but now we have it. But that time we had some limitation, but still, Mininet was good enough to do the basic research and basic work to get the prototype done in that particular time. So now I'm almost coming to the end. I think I can take 5 minutes more if the time is not already up.
No, sure, you can go ahead. You have 10 more minutes actually.
Yeah, sure. Thank you. So, okay, within 5 minutes, I will wrap up. So, very popularly, why I'm saying Google, why I'm mentioning about Google's network in this particular slide, because, as I told you, if you talk about SDN, software defined network, Google was the first one to implement SDN in the wide area network. I just told you, and Google has the one of the very largest implementation of software-defined network in their data center, in their particular inter-data center network traffic. Okay, so that's why if you want to go to the particular link, I have given in the link below the Google research from the network infrastructure. They have a team. They have a lot of obligations given there in that particular page. So you can go with the article of Google before WAN, and they have their own data center fabric that is called Jupyter, and they have also their own control plan, Orion control plan. So I think that was published in 2021 or 22, the paper of Orion, and they published in the NSDI conference perhaps. So and that was very good architecture they provided, and a little bit of diagrammatic idea of that I'm giving it here. So the first diagram is the Orion architecture. So a lot of Orion apps, like they're connecting to at the bottom we have the data plan, we have the control plan here on the top. And in the control plan, we have the Orion code with a lot of topology manager applications, flow manager and configuration managers, and SDN switches forwarding plan. That is the OpenFlow agents like OBS and all, software or hardware, whatever it is. So they are in the data plan part, and a lot of Orion apps are running here. So what they're doing, they are having some intent-based forwarding in the Orion core. This is a very basic idea of Jupyter, of the Jupyter architecture. So multiple, border routers of Orion, they are connected to the spine routers of the Orion, and multiple aggregation blocks of Orions are also connected to the fabric interconnect design. So they have, and finally from a Orion border router, fabric border router, they are going to the external network or the wide area network. And this is the earliest design of basic design of before networks. They have their multiple sites in the one data center. So in each of the particular site, in each of the sites, they have their own controllers running, and multiple OpenFlow switches are running in their own sites. And they were using the interior BGP or ISIS to communicate between the switches to the side routers, and from the one side router to another side router, and in that particular site also they have their own controller. So each and every side of the particular controller, they have their own traffic engineering, and that was controlled by the software-defined network controllers. And thereby this is a little bit of elaborated architectures available in publications you can go through. And this is what we have in our campus right now. This is only a small part of that. We have some other OpenFlow switches. You can see in this diagram, I took the picture, I think, just before I started the presentation. I went to the lab. So you see this, we have as you already know, we are also working on the software-defined network-based Internet of Medical Things setup. So what we actually have, we are using we are working on the quality of service of the IoT traffic, because we have a lot of medical service, a lot of medical sensors, and from the medical sensors, our traffic is going out, and from the ESP devices, the microcontroller devices, the traffic is coming to the Raspberry Pis, and Raspberry Pis are also having installed with OVS, the Open vSwitch. That gives the OpenFlow ability in the Raspberry Pis. You can see one of the Raspberry Pi here. So this Raspberry Pi is doing what? Looking at the packets, trying to classify the traffic, and try to do the DSCP marking. The DSCP, the differentiated service code point. So DSCP marking it does at that particular Pi, and from that particular Pi, the traffic is coming to the hardware Allied Telesis OpenFlow switches. There are two OpenFlow switches, Allied Telesis, and the third one, you see, this is the Dell EMC ONI switch that we're talking about, Right now for this work, we are not using that. We are using that for other work. So this is and there are some other switches and other racks. So we are just showing out that part. So this will give you an we have a basic quality of service implementation in this particular hardware switch because this is highly capable of handling around gigabit. It can handle up to gigabit per port. So that will give us the high-end packet processing. Suppose we have a medical checkup going on, then what will happen that from the medical sensor, we'll send out the sensor traffic. At the same time, the same patient may also go to the video consultation and may also go through some normal telephonic consultation also. So what we do, we classify the particular types of traffic at the Raspberry Pi, and after the classification, the whole traffic goes to the OpenFlow hardware switches, and then we apply the OpenFlow queues or OpenFlow meters as per the priority of the particular patient, as per the priority of the particular department. We just flow the traffic to the fog network, our cloud network we have. So we are just sending out to the fog or cloud. So this is we have our architecture in our campus. We have multiple OVSs running, and in the Dell EMC switch, as I told you, this one is the Open Network Install Environment switch. We are using the OpenSwitch operating system, and on top of that, we are using the OVS, Open vSwitch. And we have to create the bridges, and that will give you the whole switching ability with OpenFlow. And we have 5 alert analysis switches supporting both OpenFlow 1.0 and 1.3. And we have a lot of Raspberry Pis. Whenever we want a small scale OpenFlow implementation, we go with the Raspberry Pis, and we get all the OpenFlow support in the OBSs on the Raspberry Pis. So this is what small scale implementation in our case. And I think with that, I would like to wrap up my talk today. I hope. Thank you so much for giving me that time and giving me the opportunity. I'm not sure like how much I could import the things, but I believe at least that will be of some that will give you some benefit at some time if you think that okay, some knowledge I could share. And if you think that okay, there's something I can help in your research or anything, you can communicate to me in that particular mail ID. You can from my profile also. And thank you so much. If you have any questions, you can definitely ask me. I'll be available for the Q&A right now.
Thank you so much, Dr. Medhi, for this wonderful talk, and I'm sure we all learned a lot. And yeah, it is. We actually are having quite a few questions. It is
Sure,
coming
sure.
in chat box, so I'll be I'll be saying the questions, and you're free to answer them as you wish. So Dhriti Mohan Sharma asked that, good evening, sir. It is great to hear from you after long. How is SDN helping in decreasing the east-west traffic in the data center? Wouldn't the discovery packet from the controller add to the east-west traffic?
Sure, definitely. That is a very good question, I believe. See, east-west traffic, whatever I'm talking about in my slides, the east-west traffic, that is, you can say precisely, that is the induced traffic. Northeast, actually, north-south traffic is inducing the east-west traffic. And if you talk about the discovery protocols, like your BDTP protocol, your location discovery protocols, okay, so LDTP, BDTP, so those kind of protocols are there. So those kind of protocols are actually coming under the category of control protocol. Definitely, they will also add up some volume to the east-west traffic, but they are actually coming under the category of the control traffic. And when they are coming up, these discovery protocols, they are coming up at the booting up of the network. When the network is booting for the first time, these discovery protocols are coming up, and they will discover the whole topology. And the whole topology is once discovered by the controller, then they will be periodically called after some particular period. They will be automatically broadcasted, and controller will get the update from that particular broadcast. So they are definitely adding up some volume, but as I told you, they cannot be categorized directly as a east-west traffic, because east-west traffic, as I tell you right now, that is the induced traffic. Actually, that is a result of the north-south traffic most of the time. I think I have answered that particular question.
Thank you. Thank you, Professor Medhi. Santosh Das asked two questions. What is the role of AI and SDN, and what is SDN in machine learning? So I believe, like, what's the role of AI and ML in SDN? Well, how do
Sure,
you?
sure, sure. Yeah, that is a very, like that is one of the very burning question, I'll tell you, because we are also struggling in that part. Like we start a little bit of research on machine learning and AI in SDN, and only challenge is that, like machine learning, like, the speed of machine learning algorithms, the speed of computational speed of the AI algorithms. If they're running fast enough, if the ML and AI are running fast enough with the speed of network, with the speed of the packet, I just say like, with the line speed. That is say, like I have a 1 gigabit network, I have a 10 gigabit network, but if you have a latency in the ML computation or AI computation, the latency is a big problem. And if anyhow we are able to solve this kind of latency issues, that is actually speed mismatch between the ML computation and your network computation. So then I think ML and AI can give a lot of automated networking also. Because SDN is already automated, but we are programming to automate it. But if the AI algorithm takes care of it, whole SDN network is taken care by the AI, like you have the chat GPT nowadays, we have a complete AI SDN controller, then that can be a revolution because like we don't have to program also. It will automatically take care, automatically broadcast everything, automatically do the fault tolerance, failure recovery, and a lot of things can be done. So definitely this is a good sector of research. If anyone is working on SDN, that is a very good amount of research, and we are also trying to work on it. And definitely, if we keep in touch, and we can do some work together also, because we are also interested to know how actually AI can automate the whole controller operations. There are few resources available, not many, but definitely there's a huge scope in future. I can say that a lot of things can happen in future with AI.
Thank you. Thank you. Vaidehi asked 5G and IoT. Can you please brief? So I believe the question is about how SDN is integrated with 5G and the IoT ecosystem.
Sure, sure, sure. Like many of you are doing research in 5G, and like 5G core network, especially. If we talk about the 5G core network, we can do a lot of things with SDN because what is SDN? SDN is something we need to get at least something, wireless or wired, whatever. We need to get some agent which is actually supporting one of the SDN APIs. Like if I install OBS in my laptop will be supporting OpenFlow and it will be compliant with the SDN. So the thing is like that. So 5G network, 5G core network, there are a lot of things going on with the SDN because if we just do a good traffic management in the core network, especially, then our 5G performance can also enhance. And definitely, SDN will definitely is already enhancing in a lot of places. A lot of implementations are already there, and SDN is enhancing the core network performance, and thereby it will also improve the overall throughput of the 5G network, possibly. And you know that many people are talking about 6G also, and then the things are coming like a lot of satellite network kind of things and internet of space things, and those things are also coming up. They're also, like in a lot of satellite modules, people are also trying to build up the satellite network with SDN. So internet of space things, that is people are thinking one of the implementation of 6G, one of the way to implement 6G. That is also, I think people are already started thinking on working on the SDN. So whenever you have one device supporting SDN, you can do a lot of things. You can definitely optimize, you can definitely improve the whole performance. And SDN core network, 5G core network is definitely is getting benefited from the software defined network.
Thank you. Thank you so much. Maybe we have time to address one more question.
Sure, sure, sure.
Rasdeep asked that, sir, I just wanted to know what are different experimental scenarios of SDN in distributed systems.
Different scenarios in?
As different scenarios of SDN in distributed systems.
Sure, like like distributed system, like most of the problems of distributed systems in like synchronization issues and a lot of things are there. So definitely, SDN is not limited to a single controller or centralized design. We have a lot of controllers, we have a lot of designs that is giving the distributed software defined network. or distributed controller design. Like if you heard about the ONOS controller, one of the very popular distributed controller design, that actually are distributed system. There are a lot of problems. So those problems can be also resolved by the distributed controller design. We already have a lot of controllers in that, like ONOS and few other. And I think you can go to OpenFlow specification 1.2 and 1.2, 1.3 and others, and the higher versions. They have the facility of like controller role, like master controller, your slave controller, equal controller. So controller role switching is also available, and that is also suitable for any kind of distributed control, distributed system architectures. So we have the ability to do that, and distributed controller design will try to address that kind of distributed system issues.
Okay, thank you. Thank you so much, Dr. Medhi. Maybe we'll close with a question, short question of my own. I was just
Sure, sure,
wondering
sure.
that, so one of my area of research is also SDN. So I
Great,
am
that's good to know.
personally, I was very interested in your talk and I listened in like, all the things that you presented. It was wonderful. I learned a lot. I was just
Thank you.
wondering, like, and it always confused me, the P4 and the open flow, the P4 data processing, or the P4 packet processing and the open flow. So are they same or are they different, or like what is it? Like I always get confused between what is P4 and what is open flow. Like both to me seems like we have some ingress packet coming, some data processing, some match rule happening, and some egress packets going out. So just maybe a hint on this.
Sure, sure, sure. That is definitely a good query only. Because you know already SDN. So what I say that SDN we have the layers, right? Control plan, data plan, and all those things. Now just start thinking from the data plan, not from the control plan. If you get a bottom up approach, then just look at the data plan. So when I use the OpenFlow controller in one side, and another side we have P4. So in the data plan, we have no difference at all. Because when I talk about the data plan, the forwarding circuit I'm talking about, then OpenFlow is doing what? Is OpenFlow controller is instructing the control plan, and control plan is installing the policies on the data plan. So ultimately, data plan is following the same thing. In P4 also, same packet processing, same things, same policies are implemented in the data plan. So from the data plan level, no difference at all. But in OpenFlow, what happens? We have the control plan communication required to the data plan, and control plan to controller, control plan to data plan. That additional communication is required, and we are controlling from the controller side itself. In P4, what we do, we are already debugging, we are already compiling the policies in a different system and directly importing the policies to the switch. So what is happening? Those policies are running like some of the system programs. Some of the configuration system program, like you have the DLL files, in a lot of operating with the DLL files and all those things, middlewares and lot of things are there, driver files. So they are actually operating like those policies are installed as a file, and those policies are operating on the forwarding circuit. So ultimately, from the data plan perspective, OpenFlow and P4 working in the same way. But if you go above the data plan, then we have the different type of communication in OpenFlow, because OpenFlow is controller to control plan to data plan, and here we are doing what? We are system debugging and directly putting in the data plan. But the only problem we are facing right now, we are also facing, because whatever I think if you use the BMD2 model for P4, and whatever is already available in open source, the V1 model of P4 debugger, that is very low scale. That is not scalable enough. So whenever we do research in P4, we get a very low throughput. We also implemented very low throughput in OBS and all those things, but it is the whatever distribution is available, that is not highly scalable. But if it is highly scalable, if we get a good implementation of, like I already told you the example of smart NICs, like Xilinx, FPGA. There are some of the boards that will support the smart NIC features, and also the Xilinx have a smart NIC with P4 support. If we get a hardware P4, then definitely you will get some advantage of P4 over OpenFlow, because that will be faster.
Yeah, thank you. Thank
Right
you
now,
so
it is not
much.
faster. Yeah.
Yeah, so yeah, I have few questions requesting the for flow Devorsi asks. Okay, unfortunately, we are really short on time, so I would like to request Devorsi to directly mail Professor. Okay, if is that is fine, Dr. Medhi?
Yeah, I think sure, sure. Anyone can mail to me, like if you have some
Yeah, yeah, yeah.
question. or I will definitely, I'll promptly reply to the mail, and
Sure, sure, sure. I will. I also look forward to interacting with you. So,
sure.
Devarshi,
And I'll
please
also share the
mail
PPT.
Professor, and he'll directly get in touch.
Yeah, sure, sure. Thank you.
Okay. And we have a request of sharing the slides. So if it is not a maybe you
No, no,
can.
no, not a problem at all. I'm doing it right now, only within 5-10 minutes after closing the show. Okay, so that's not an issue.
Okay. Thank you so much, Dr. Medhi. Can you just unshare your screen? I would like to share mine.
Yeah, sure.
Yeah. So on behalf of the CSSBC and all the participants present here, so again, thank you so much for your wonderful talk and presentation. We learned a lot, and on behalf of our CSSBC, I would like to present you a token of appreciation as well as a virtual memento. So I would share my screen now. So if this is visible, then yeah. So,
Oh,
sir,
that
this
looks
is for
good.
you. Thank you so much on behalf of SBC.
Thank you.
We had a wonderful session, and as a last request, I would like to ask all the participants if it is possible to please switch on their cameras. The maybe I would like to request to we'll take a screenshot. Okay, if it is possible, of course, like no force or something, only if it is possible.
I see a lot of known faces because I see Dipankar there. He was my student only, right, like in MTech. So some of the faces are known. And definitely, I heard about your lab and your all the research work. You're doing really great, and I really like to interact with you in future also. Please communicate to me. I will
Okay,
also learn a lot from you.
okay. Just a minute. I'll just take it. Yeah, we have it. Thank you so much, all the participants. We have the screenshot. So once again, Dr. Medhi, thank you so much for delivering the talk, and we all had a wonderful time. We look forward to meeting you, sorry, connecting with you soon, and hopefully we'll meet also physically someday.
Sure. Thank you so much. Thank you so much for the opportunity. And good
Bye.
night to all.
Good night. Have a great day. Bye bye.
Bye.